the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds.
Good morning and a warm welcome to this session on spatial data, where we will have 6 excellent papers on different aspects of cartography and looking at different degrees of geographical abstraction. So a really fascinating session ahead. My name is Aidan Slingsby from City University London, and it's a pleasure to chair this session. Okay, the first paper in the session is going to be presented by Magnus and some of his other authors, and they will describe their work that automatically shades maps, which makes them as good as those created by professional cartographers.
We are a team of colleagues at Monash University in Melbourne, Australia and ETH Zurich in Switzerland. Together we show our research on cartographic relief shading with neural networks. This is an excellent example of a topographic map created by SwissTopo, the Swiss National Mapping Agency. All map elements have been carefully optimized for readability. However, the map in this form does not clearly show the third dimension of the terrain. The map contains contour lines, but extracting elevation from contour lines is tedious and difficult. When a shaded relief image is added, the shape of the terrain is very clearly visualized. We can immediately distinguish between low valleys and high mountains, and we can also identify small details, for example smaller valleys or landslides. Shaded relief is very effective at different map scales. Here we see a detailed map at the large scale showing a small section of the Jura Mountains in Switzerland. Drawing shaded relief requires specialized expertise. Here is a time-lapse showing cartographer Sarah Bell drawing a shaded relief image. She uses pencils, but even when using digital image editing tools, creating high-quality shaded relief is immensely labor-intensive. Experts at SwissTopo have perfectioned the art of cartographic relief shading. Here is a SwissTopo cartographer spraying a shaded relief with an analog airbrush. This results in outstanding shaded relief images, such as this piece of art that very clearly shows the structure of the main landforms. Our goal was to develop a digital method that creates shaded relief images of similar quality from digital elevation models. We developed a neural network that improves on existing algorithms. Here is an example output of our neural network. We trained the network with a manual relief shading of Switzerland and then applied the network to a digital elevation model of the Caucasus Mountains. In our presentation, we will first look at design principles that cartographers apply when manually shading a terrain. Then we will discuss the architecture of our neural network and describe how we trained the network. Then we will show how the shading can be controlled to adapt results to the characteristics of the terrain. And finally, we will show results of an evaluation that we conducted with expert cartographers.
Cartographers have developed a series of design principles for creating effective shaded relief images. We start with briefly reviewing these principles because they guided our research. This is again the manual shading produced by Eduard Imhof and Heinz Leutzinger. Let's analyze what design principles they used when creating it. The general direction of illumination is from the top left. This reduces the chances of relief inversion. Relief inversion may occur when the terrain is illuminated from the bottom. With relief inversion, mountains are perceived as valleys and valleys are perceived as mountains. However, with an illumination strictly coming from the top left, not all terrain forms are illuminated in the best way. This mountain is a good example. Its main ridge is in northwestern direction, which aligns with the top left illumination direction. As a result, both sides of this mountain would receive the same amount of illumination, and both sides would be shown with the same gray value. This major mountain ridge would be barely noticeable. To avoid this, the cartographers adjusted the direction of illumination. This is the local direction of illumination used for drawing this shading. So instead of this regular top left illumination, the cartographers adjust illumination throughout to show each landform with the best light. Another important design principle is highlighting of large landforms. The terrain is structured in major illuminated slopes and also shaded slopes. Illuminated slopes are brightened and the shaded slopes are darkened. This results in this clear structure where mountains are grouped and valleys are clearly visible. So, in essence, the brightness of an individual pixel is determined by shape and size of the landform of which it is part of. Generalization is the abstraction of information with scale. Here is an excellent example showing the Aletsch Glacier in the Swiss Alps. The characteristic shapes of the landforms are shown at all scales, but the level of detail gradually changes with scale.
We experimented with different neural network concepts such as encoder-decoder networks and neural style transfer. Finally, we found that the unit architecture shows the most promising results. Originally, the unit was introduced by Ronneberger et al. In 2015 for semantic segmentation. Here you can see what our specific version of the unit for terrain shading looks like. In essence, the unit maps a tile of a digital elevation model to a shaded relief tile covering the same area. This is being carried out by a sequence of convolutional layers that gradually modulate the input image until the output image is obtained. In the final layer, a cropping operation is performed, effectively reducing the size of the tile for which the predictions have to be made. This is necessary, as the correct grayscale values of the relief shading tile are highly context dependent. For the cropped pixels, it is assumed that not enough context information is present to enable the neural network to make correct predictions. A sequence of convolutional layers alone is not able to capture enough context to make informed predictions. Hence, convolutional neural networks typically also employ pooling layers to gradually generate compact representations of the input image. The stepwise combination of pooling and convolutional layers make up the so-called contracting path of the unit. The feature representation needs to be scaled back to the dimensions of the target tile. This is being carried out by the expanding path, which employs several convolutional and deconvolutional layers to gradually increase the spatial dimensions again. Constructing a relief shading tile from a compact representation often lacks fine-grained local information in the final image. By combining activation matrices of the contracting path with the matching activation matrices of the expanding path, it is possible for the network to analyze both high-level and low-level information. This results in locally more accurate relief shadings.
We trained various networks with shaded relief images created for maps at different scales. For example, here we see the 78 sheets of the Swiss TopoMap series at a scale of 1 to 50,000 that we used for training. Here is a section of this shaded relief. For training the networks, we used standard GPUs. We used images and elevation models that measured up to 16,000 times 10,000 pixels. We ran up to 5,000 epochs, which required up to 5 hours of training.
The neural networks for relief shading do not have parameters that can be tuned directly, but we can adjust how we use the neural network to control the output shaded relief. When computing a shaded relief, a trained neural network reads an elevation model, such as this one, and computes a shaded relief image. It applies the light direction that it learned during training. Sometimes it's useful to adjust the direction of illumination, for example, when we want to imitate the natural southern illumination direction on the northern hemisphere. This can be achieved by first rotating the elevation model, then shading the rotated elevation model, and then rotating the shading back to the original orientation. The result is a shaded relief with southern illumination. Of course, we can use any angle of rotation. We train neural networks with elevation models and shadings of Switzerland. Here is what happens when we apply one of our networks to the lowlands of northern Poland. This rather flat lowland is shown almost like an alpine landscape, with strong contrast and sharp edges. This happens because the elevations of this lowland are scaled to the elevation range of Switzerland. Here we only use the lower 20% of the possible elevation range. As you can see, contrast in the shaded relief is reduced, and the lowlands are more accurately portrayed. We can control this level of generalization with two methods. Here, we simply downsample the cell size of the elevation model and apply the same neural network. The network learned to retain and accentuate sharp mountain ridges, so the shaded terrain does not appear blurred, even with the larger cell size. Here is a second method for generalization. We trained 3 neural networks with elevation models with different cell sizes. The 3 images here were created by applying the 3 neural networks to the same elevation model. The neural network that created the image on the left was trained with a low-resolution elevation model. It learned to retain as many details as possible. The effect is that the shaded relief shows many details. The neural network that created the image on the right was trained with a high-resolution elevation model. It learned to discard information and only retain the most essential shapes. The effect is that the shaded relief only shows the most important landforms.
To evaluate our results, we conducted a study. 18 relief shading experts participated. We selected 10 high-quality shaded relief images that were produced manually. We then created corresponding shaded relief images of the same area with our neural networks. The experts were asked to rate the images of each pair. These are the 10 pairs of relief shadings. Let's have a closer look at what the experts thought about them. For each pair, we asked them to indicate which of the 2 shaded reliefs is better for a topographic map. We did not tell them which image was created with a neural network. For 5 of the 10 pairs, the experts preferred the neural network shading. Here's an example. On the left is the preferred neural network shading, and on the right is the manual shading. For each pair, we asked experts to identify the shading that was aesthetically more pleasing. The answers were similar to the overall preference. Here is an example, where the experts found the neural network shading on the right to be more pleasing than the manual shading on the left. For each pair, we also asked experts to identify the shading that was produced manually. In general, they found this difficult. 3 pairs were particularly difficult. Here's the one of these examples. The neural network shading is on the right.
We now come to the conclusion of our presentation. We have proposed a neural network architecture that can create high-quality shaded relief. An advantage compared to other digital shading algorithms is the consistent and visually pleasant generalization of terrain. Another advantage is the direction of illumination is adjusted to highlight important landforms. In summary, we hope to contribute to the curation of cartographic relief shading and bring high-quality shaded relief to the reach of modern mapmakers. We would like to thank the National Geographic Society for supporting this research project with an exploration grant. We also thank the 18 relief shading experts who participated in the study and the anonymous reviewers for their comments and suggestions.
Thank you very much. That's really beautiful work, and it's nice to see most of the presenters, most of the authors presenting this. Magnus is here to answer our questions. So there are lots of nice comments in the chat about how well explained the work was and how good it is. There's a question from Joe Wood about, so he asks, he notes that scaled relief is a measure of multi-scale morphology, and could this approach be adapted to characterize other multi-scale geomorphological features such as curvature and feature classification?
So if I understand correctly, you want to
somehow use a machine learning approach to classify, for example, different landforms. And if this is the question, if I understand correctly, then actually we were thinking in the same direction. So to somehow either to try to use an autoencoder to explore the latent space, or also to really use a similar architecture that we just showed to really get high or low level features out of the DTM.
Okay, thank you. There's a question from Annika as well, who asks, why do we need machine learning? Can we not just render a physical 3D model and then use normal lighting conditions?
Yeah, well, actually, a lot of things have been tried already. I think this is one of the approaches that also was carried out at our institute. And to be honest, I may not be the perfect person to explain why something is good or bad, but when we showed these to cartographers, especially those that worked at the atlases, they were never really satisfied with the results. They were always pointing towards the Imhoff reliefs or the ones by Swiss topo. So it was somehow straightforward to us to try to replicate those rather than going further in the direction of these kind of models.
Okay, thank you. Another question is, how much artistic interpretation do cartographers use when they're shading maps? Do cartographers make choices that, do they always make the same choices?
I don't think so, actually. So, I mean, there are some general rules that are probably followed, but in the end, it's very individual work. So you can give two different cartographers the same piece of a DTM and they will come up with some somewhat different shaded reliefs, I would guess.
Okay, great. Well, thank you very much. We're going to move on to the next paper now. So
thank you too.
Thank you very much. Okay, the next paper. This paper got an honourable mention, so I'd like to congratulate the authors for this. The title of the paper is A Simple Pipeline for Coherent Grid Maps, and Max will be presenting a comprehensive approach for generating good tile maps. And I really like this work because it goes through the design criteria one would need when designing grid maps, and then it demonstrates really nicely a method for producing those. So let's see the paper now.
Everyone, and welcome to this video presentation of a simple pipeline for coherent grid maps. To start, I'll first explain what a grid map is and what I mean by coherence before explaining how the pipeline works. A grid map is an arrangement of simple tiles that represents a geographic area subdivided into regions. An example is shown over here. On the left is a map of the local authorities of the United Kingdom. On the right, a grid map of these authorities is shown. Each region is turned into a tile, and these tiles are arranged such that they reflect the underlying map. Grid maps are used to visualize spatial data by region, and are often used by, for example, news outlets, other companies, and academics. Examples include the Washington Post and the New York Times using grid maps for the United States. Zeit and Line made a grid map for Germany, and Rod Redburn made one for the boroughs of London. Triangular grid maps also exist, such as this one from McNeill. In academia, we see more complex designs to support spatial data analysis, such as this map visualizing the dynamics of London bicycle hiding scheme. In this so-called OD map, each tile is even used to yet again show the entire input map. One can make many different grid maps for the same input map, but what determines whether a grid map is of high quality? A high-quality grid map should be coherent with the underlying spatial dimension. There are many facets of coherence to consider, which we'll illustrate using a small map. We identify each region with a small colored representative point. One facet of coherence is the distance. Ideally, distances between the spatial elements in the map correspond to the distances between their associated tiles. This is illustrated by these two grid maps. In the middle grid map, the distances are roughly maintained, and it's quite easily to correlate the input map to the grid map. In the grid map on the right, however, the distances are distorted. The green square is much further from the other square, which makes it harder to link them. Displacement relates distance between the input polygon and tiles placement region. Ideally, we want tiles to be positioned closely to the point that represents the region. In the middle figure, the tiles are indeed much closer to the original position compared to the grid map on the right. While displacement is not a facet of coherence by itself, it's often used as a proxy for distances and the other facets of coherence. Another facet of coherence is that the adjacencies between the regions should be preserved. In this case, the orange region should thus be adjacent to the blue and red region, while not being adjacent to the green region. We cannot always maintain all adjacencies. However, we would like to ensure that they are at least continuous. Thus, tiles should not be separated from the rest if the input is contiguous. In other words, we should not suggest islands when they're unknown and vice versa. Good grid map also preserves the direction between the regions. In our example, the orange region should be thus to the right of the blue and the red regions, and not to the left. One advantage of many grid maps is that they resemble the overall appearance or global shape of the input region. This helps a viewer to identify the region of interest more easily. In this example, the input has a rough T-shape, and this should be present in the grid map as well. However, with tiles being such that their arrangement resembles the input, we also obtain recognizable features, and thus we also need to ensure coherence with the local shape. That is, tiles that are on identifiable positions in the grid map should match to regions on identifiable positions in the input map. In our example, the rightmost tile is easily identifiable and matches with a part of the input shape that contains the orange region. Thus, we want the rightmost tile to be assigned to the orange region. Ideally, we would like to adhere to all of these facets simultaneously. However, this is not always possible in practice, and therefore there exist different algorithms for it. For grid maps, one can distinguish between two different map types, simple and complex maps. On the left is an example of a simple map, the departments of France. The shape of France is mostly convex, and many of the departments have a similar size. On the right, we have the municipalities of the Netherlands, which is considerably more complex. First, the isomer as shown in the circle here is a large characteristic feature, which makes the shape decidedly not convex. Furthermore, we see large variations in municipality sizes across the country. If you compare, for example, the northern with the southern municipalities, the northern municipalities are generally larger. Existing grid map techniques mostly work for simple maps, which we'll briefly go through before moving on to complex maps. For simple maps, one can use a point set matching algorithm that minimizes displacement from regions to the tiles. As an example of how this works, we start with the departments of France. We first represent each region of France by a representative point. We then no longer need the region itself, so let us focus on the point. We overlay a grid over these points that represents the possible tiles of a grid map. And we then use the point set matching algorithm to assign each point to a tile in such a way that the displacement is minimized. The predominantly short arrows suggest that we have a good layout of our tiles, with comparatively little displacement. The assigned tiles together form the grid map of France. If we compare the grid map generated to the original map, we also see that the global shape is represented well by the tiles that have been selected. The point setting matching algorithm generally works well for simple maps, but struggles to deal with complex cases. So let's return to the case of the Dutch municipalities as an example of a complex map. If we follow the same approach as for simple maps, we get the following grid map. Though the displacement is minimized, the result does not satisfy the basic requirement for contiguity. One way to solve this is by computing a shape of tiles that match the Netherlands well in terms of shape, and then minimizing the displacement using only these pre-selected tiles. While better, this is not ideal either. If you look at the region within the circle, municipalities cross from one side of the lake to the other, which strongly violates the local shape facet. To solve this, one could try to use a more shape-aware displacement metric, such as geodesic distance. This does not quite solve the problem yet. Municipalities still end up on the other side of the lake, although they now shift alongside its boundary instead of crossing it. What we need is a method that can cope with the underlying source of the issues, strongly varying region sizes combined with a complex shape. Our pipeline nicely resolves these problems with complex input maps. Before we go there, we'll first explain what are the techniques that exist for complex maps and explain the limitations of that technique. The technique is from McNeill and Hale's paper, Generating Tile Maps. Roughly speaking, their technique works by first redistributing the points to achieve a more uniform spread. For example, the regions near London will be spread out, and the regions near Scotland will be pulled in. The input shape is then dragged along with the points. Finally, tiles are selected within this deformed map, and displacement is again minimized, which results in the grid map on the right. We identified two limitations of their technique with respect to all the facets of coherence. One is visible in this grid map of Denmark generated by the technique. If you look at the highlighted region, it's discontiguous, giving the idea that there are two islands present in the brown region. However, the regional shape is connected. The second limitation relates to global shape and can be seen in the grid map of the UK. If we look at the highlighted region of Scotland over here, then the grid map does not resemble the salient features of the original map. On the right is the result of a grid map of the UK using our pipeline. Here, the global shape of Scotland is better preserved. This issue is also present in other parts of the map, for example in the shape of Wales and in the Thames estuary. The loss of these salient features of the global shapes makes the map harder to recognize as a grid map of the UK and also removes important reference points that can prove local shape. For these reasons, we present a new algorithm to compute coherent grid maps for complex maps. We propose a simple pipeline, basing each step on existing techniques. As the first step of our pipeline, we decompose our complex input map into simple parts. We do this for each connected component of our input map as follows. We start by generating a set of candidate cuts following standard principle shape decomposition. From this large amount of candidate cuts, we select cuts such that the resulting parts are both visually salient and have enough tiles such that we can represent the shapes. This gives us the cuts highlighted in red. Getting rid of the rest of the cuts, we now have the cuts we use in our partition. We repeat this process for every component separately and include how many points are in each part. I'll go back to our pipeline. So we've now decomposed our input map into simple parts, and as the next step, we're going to represent each part with the correct number of tiles, while maintaining the contiguity and the global shape. This results in a tile arrangement. To do so, we apply the technique of mosaic cartograms, designed to solve this problem in the context of generating tile-based cartograms. The part highlighted on the left is represented by the tiles on the right. The shape of the tiles on the right roughly matches the part, and as mosaic cartograms seem to work well in practice to represent these parts individually. Moreover, looking at the highlighted region, it can also maintain the global shape, including highly non-convex features. After we generated the tile arrangement, there's only one more step in our pipeline, and that is to assign the regions to the tiles in the tile arrangement. We do this by optimizing the displacement. Let's zoom in on what we need again, and we're going to illustrate this for the 4 regions in Flevoland. On the right are the 4 regions. We overlay the tiles with the regions as well as possible. Then we assign each region to a tile, similar to before, and this gives us our assignment for this part. Repeating these steps for each part gives an assignment for the entire Netherlands. And this is our entire pipeline. Our pipeline just starts with decomposing the input map into simple parts. We then represent each part with tiles, and finally we optimize the displacement of the assignment from regions to tiles for each part separately. Our pipeline is able to generate high-quality grid maps for both simple and complex maps. An implementation is available online at the links shown here. Maps shown here are examples of our pipeline on different maps. I would like to thank you all for viewing this video, and if you have any questions, I'll be happy to answer.
Great. Well, thank you very much for presenting that paper. There were lots of very good comments in the chat. People really liked the way it was explained and liked the work. I've got a question about distortion. So, of course, all maps to some extent are distorted because we're projecting from a sort of sphere to a plane, and different map projections prioritize angle or distance of other measures. Your maps, because of the other characteristics, they don't preserve distance from the original places as much. Is it possible to change the weightings of the different criteria?
Good question. So currently in the process, not. So the way the process works is you can change the cuts to figure out which parts you want to present more. The second step of the pipeline, which could be replaced by a technique that does it, but it's currently the mosaic map, which mostly optimizes for adjacency and global shape. So there's no implicit distance in there that you can tweak around. So you would have to have a different technique that gets the correct amount of tiles for a simple region and optimizes for this distance in there.
Okay, so I guess you can adapt different parts of the pipeline depending on what you want to achieve.
Yeah. Yeah, so essentially, if you think that one part of the pipeline is not suitable for your process, then you could, in principle, replace it by something that does that part better.
Okay, great, thank you. There's a question from Kevin in the chat. Do you have any examples of the best and worst bits of your algorithm?
Best and worst fits. So I do have a couple of best and worst fits. There are a couple in the paper as well. There's a table in there of different parameter settings and the different results they give for that. We of course have lots more data that we generated over time. That if you're interested in it, I could send it to you and you can have a look at it. But, yeah.
Are there any really difficult countries?
Difficult countries. So the world in general is a bit difficult, mainly because Russia is so far stretched and adjacent to so many countries and only has a single square. Most things we tried it on are relatively well shaped. So the more complex maps that have, as the Netherlands, which have holes in them, or that are really, so they're elongated. So essentially, if it's a simple map, it works pretty well from standard techniques. But the more complex map that you might have to do something in a partition manually. Usually it works just fine if you use it.
Okay, great. Thank you very much for your paper. Well done.
Thank you.
Okay, we're going to move on to the next paper now. So this will be presented by Sven, and he'll be talking about a method for designing interactive maps to let people look at the names of points on maps in very dense point maps. So it's for labeling very dense point maps. So I'm going to hand you over now to his talk, and he'll present it. He'll explain it better than I just have.
Hello, my name is Sven Gedicke from the University of Bonn, and my today's presentation is about Zoomless maps, external labeling methods for the interactive exploration of dense point sets at a fixed map scale. This is joint work with my dear colleagues Annika Bonerath, Benjamin Niedermann and Jan-Henrik.
I want to start with a short motivation. Imagine traveling to a foreign city and searching for good places to have lunch. A common procedure is to take out the smartphone or even a smartwatch and get a rough overview of the city first. By zooming and panning the map, the actual area of interest is fixed and results are queried using a suitable search term, for example, restaurant. The queried results can now be explored. Due to the limited area of display, it can easily happen that the map is cluttered with results and individual labels are not sufficiently visible. A common approach to overcome this problem is to zoom in and out to retrieve all queried information. However, this has the disadvantage that the map extent and scale is changed frequently and the overall map context may be lost. This is the point where our research comes in. Today, I present an alternative approach called Zoomless maps. Instead of zooming in and out, a user is provided with different specialized interaction techniques for exploring the queried results. The general idea of Zoomless maps is that all information available in a current map frame can be assessed while the map scale is kept fixed. In previous research, we distributed the information on multiple pages using internal label placement such that no labels overlap. In the example on the right, 6 pages were used which the user can browse through by clicking the buttons. Once the 6th page is reached, the user can be sure that he or she has assessed all information. An advantage of the internal label placement is the clear association of labels and features. However, it can cause the underlying map to be strongly covered when using large pictograms or even images as labels. Additionally, there is no possibility of presenting the information in a specific order, for example in descending order of restaurants' ratings. Therefore, as an alternative, we consider external labeling methods for Zoomless maps. More precisely, we developed 3 different approaches, namely multi-page, sliding, and stacking boundary labeling. In the following, I will give a short demonstration of each method. In all 3 methods, the labels are arranged at the bottom side of the map and they are associated with their point features via connecting leaders. In multi-page boundary labeling, the labels are distributed on multiple pages, such that each page consists of a boundary labeling. The user can navigate through the pages by using the navigation buttons. In sliding boundary labeling, the labels are arranged in a single row that can be continuously slid along the bottom side of the map. Only labels directly below the map are displayed to the user. Our third method is stacking boundary labeling. In this method, the labels are distributed on stacks such that each label belongs to exactly one stack. Only the topmost label of each stack is associated to its point feature via a leader. When the user clicks on a stack, the topmost label is pushed underneath the bottommost label. Hence, the second topmost label moves up and is then connected to its point feature. Generalizing all 3 approaches, we built a unified algorithmic framework. We assume that we are given a set of point features, each of them with a weight. Using the running example of restaurants, this weight might represent a user-given star rating. At the bottom of the map, we define k fixed positions, called ports, where we attach the labels of features. A feature and a label are associated via a leader. Further, we define a state as a mapping of each port to a point feature. A labeling is then a sequence of else states. In a preliminary study where we asked experts to comment on draft versions of our approaches, we received a lot of feedback that we used to set up the following optimization criteria. As a user might be interested in exploring important features first, front states should contain features with higher weights than back states. Considering the labeling of restaurants, high-rated restaurants should be labeled earlier than low-rated ones. Further, the intersection of leaders should be avoided, as these can affect the traceability of labels and features. For this reason, small vertical distances between leaders should also be avoided. As a fourth criterion, the overall length of leaders should be kept short in order to provide a clear map representation. I will focus on one of our 3 approaches in the following, that is, sliding boundary labeling. The idea of this approach is that the labels are arranged in a single row below the map. The user can slide the labels continuously from left to right to explore all labels. Displayed are only the labels directly below the map, such that the association of labels and features is clear. The transition between two consecutive states is animated as shown in the small example on the right. Starting from a state Si, the labels and leaders are shifted in sliding direction till the following state is reached. Getting now more into the model of sliding boundary labeling, we search for a sequence of states satisfying the following requirements for valid transitions. The transition between two states is only valid if the labels are shifted left by one port each. In addition, a new label must appear at the rightmost port. Taking into account the optimization criteria I introduced earlier, we consider them in sliding boundary labeling as follows. We model the importance criterion as hard constraint, such that the features are labeled in descending weight order. As we use discrete weights, there is still much optimization potential within groups of labels having the same weight. Both the crossing and the distance criterion are modeled as soft constraints. We do not consider the length of the leaders as, except for the last k-1 labels, each label is shifted once from the rightmost to the leftmost port. Considering label 5 in this small example, one can see that there is no optimization potential regarding the length of the leader. Using our introduced model, we now formalize sliding boundary labeling as an optimization problem. Preserving the overall weight order, find a labeling minimizing the shown B-criterial objective function and comprising only valid transitions. With alpha, we specify a balance factor between both parts of the objective. CC is the cost for leader crossings defined as the normalized number of crossings. With CD, we define the cost for small vertical leader distances, considering only pairs of features whose leaders run above each other, as can be seen in the figure. Next, I will come to the approaches that we use to solve the optimization problem. On the one hand, we developed an exact algorithm implemented as an integer linear program yielding optimal solutions. On the other hand, we implemented an efficient heuristic using a hill climbing approach. We evaluate the quality of the heuristic by comparing the approximate solutions with the optimal ones. Following, I will shortly present the concept of the exact approach. Using a graph-based method, we model our optimization problem as constraint orienteering problem. To that end, let G be a directed graph containing a vertex for each possible state. Two states are connected by an edge if and only if the transition between these states is valid. Additionally, the graph contains a source vertex sigma and a target vertex tau that are connected to each state by an edge. Modeling an orienteering problem, we now search for a path from sigma to tau, minimizing our objective function and yielding a sequence of states. While for sliding boundary labeling, we implemented both an exact integer linear program and an efficient heuristic, for the other two methods we developed an exact and efficient algorithm each. However, in the following I will keep the focus on the evaluation of the algorithms of sliding boundary labeling. First, we evaluate our exact approach. We created 100 instances, each containing 30 randomly sampled features. We ran our algorithm for alpha equals 0 and alpha equals 1, which means solely minimizing the crossing cost and the distance cost respectively. As an intermediate trade-off between both costs, we choose alpha equals 0.5. Additionally, we generated a valid random solution and maximized the objective function for alpha equals 0 and alpha equals 1 in order to get the worst possible solutions. We used these results to investigate the potential of optimization. Comparing the maximized number of crossings, displayed in red, and the minimized number of crossings, shown in green, the amount of crossings can be reduced by 65%. Even when choosing alpha equals 0.5, which is displayed in orange, such that the distance cost is taken into account as well, the reduction is still 63% compared to the maximum number of crossings and 44% compared to a randomly generated solution. Similar results can be observed for the costs for small vertical leader distances. In summary, we state that there's a high optimization potential for both considered cost terms. Next, we evaluate the quality of our heuristic by comparing the scores of its solutions with the optimal ones gained from the exact approach. We observe that for alpha equals 0.5 and alpha equals 1, the costs are higher by only 10% on average. More precisely, over 90% of the instances that were tested have relative costs less than 20%. Hence, we deem the quality of our heuristic approach to be satisfactory. Next, I want to give a short comparison of all our three external labeling methods. The upper table contains the key properties of each method. We would like to emphasize that none of the methods prevail the others. Instead, we want to provide a decision support suggesting for which scenario which method is more suitable. For example, for crossing-free labelings, multi-page and stacking boundary labeling are preferable, while sliding boundary labeling might be more suitable when focusing on the weight order. The lower right table shows the running times of the efficient algorithms for different numbers of ports and instance sizes. We can observe that each of the running times is less than 1/10 of a second, which we deem to be sufficient for application.
Coming to the end of my presentation, I would like to summarize our key contributions. We develop new external labeling methods that allow a user to navigate through dense sets of point features in Zoomless maps. Our models and design decisions are based on expert advice, and we provide a generalization of all three labeling methods into a unified algorithmic framework. For each method, we implemented efficient and exact algorithms. For future research, we plan to investigate how the labeling methods can be combined with operations such as zooming and panning, such that different map frames have similar labelings. Additionally, a user study is planned to prove the applicability of our models. I would like to end my presentation by inviting you to try out our methods by yourself in our online demo. Please use the QR code to my right to get there directly. Thank you very much for your attention, and feel free to contact me for questions or suggestions.
Okay. Thank you, Sven. And yes, you did indeed describe your paper better than I did, so that's to be expected. So it's a really nice, clean design, and I like the use of your constraints because it adds flexibility. There's a question from Tim Dwyer that got lots of likes, which was that he was very excited by the idea of the sliding boundary labeling. And have you thought about putting it on multiple sides of the screen?
Yes, indeed, this is a good idea that we considered as well. I think this is a good thing to consider in future research. I think because we had so much ideas of models that we wanted to test, this would have this would have become too much for this paper. But indeed, it would be very interesting to evaluate and to see how it will work on other sides of the map.
Good.
Indeed.
Okay, thanks again. Okay, we're going to move on to the next paper, which is by Yalong. He's going to talk about how to use, he'll be comparing color and height for encoding quantities on a map in an immersive setting. So I'll hand over to Yalong now.
Thanks for coming. My name is Yalong Yang from Harvard University. Today, I'm going to present you the tilt map, a novel interaction technique in immersive environments for transitioning between multiple visualizations. This project was collaborated with Tim Dwyer, Kim Marriott, Bernhard Hurni, and Sarah Goodwin. Carplas maps have been widely used. For example, the population density around the world, the unemployment rate in the United States, the birth rate in Europe, and many more. The basic idea of a Carplas map is using colors to encode numbers from low to high, and then assigning different colors to their geographic areas. Here we are looking at the population density of the UK. There are other ways to encode numerical values. Past studies have found some encodings are more effective than the others. We can see color is not a very effective encoding, while the most effective encoding is height. As Carplas map is created by using color to encode values, we can also encode the value with height, and we will get a prism map. Carplas map is familiar to people, however, they use an ineffective encoding. Prism maps use an ineffective encoding. However, occlusion is inevitable in this representation, especially when seen from the side. It is also possible to use both color and height. In this paper, the first question we want to answer is, which one is a better choice? We found limited user studies investigating this issue. Furthermore, these studies were conducted on 2D screens. Their participants were only allowed to have one viewing direction. Their participants might suffer from occlusion and perspective distortion. We believe occlusion and perspective distortion can be alleviated in an immersive environment where the user can easily and intuitively change their viewing position and direction via body movement or object manipulation. The user can easily find the optimal viewing position and direction in an immersive environment. To systematically compare the effectiveness of Carplas and prism maps with and without color, we designed and conducted a control user study to evaluate them in an immersive environment. We identified tasks from known map tasks and previous studies. The first task we tested was an elementary task. Basically, we asked our participants to compare two values, but instead of only identify the larger one, we asked them to estimate the difference between the two. We expect this can give us a more nuanced understanding of the performance. We also tested another summary level task. We asked our participants to estimate the population density of a few contiguous areas. Again, we asked our participants to provide us a numerical result. To reduce learning effect, we used different data for each trial. To ensure the generated data reflect real-world patterns, we controlled the moron's eye of each data. Now, let us look at the results of every comparison task. The x-axis is showing the time and the y-axis is showing the absolute error. The lower means more accurate. Here, we are looking at average performance of Carplas map. Project it to the x-axis, you will have the time, and project it to the y-axis, you will have the accuracy. We use arrow bars to indicate the 95% confidence intervals for both time and accuracy. Let us look at the performance of the other two conditions. We can see Carplas maps were faster, but prism maps were more accurate. Let us check the other task. We get very similar results. We can also split the results by the size of datasets. Again, similar results appeared. We then look at the angle of the visualization. We found patterns that people would expect. Our participants placed the Carplas map vertically most of the time, while they frequently tilt the prism maps to see from the side. Our participants also ranked the visualizations in terms of visual design and readability. We use arrows to indicate that there is a statistically significant difference between two conditions. We can see participants did not like the monochrome prism maps at all. They also preferred the colored prism maps over the Carplas maps in terms of readability. We also asked our participants to rate their subjective confidence for each condition. Participants felt more confident with colored prism maps than the other two conditions. We believe this may be because the participant can confirm the answers with two different encodings. In summary, we found Carplas maps were faster, but less accurate. Prism maps were slower, but more accurate, and participants clearly prefer colored prism maps. As each view has its own advantages and disadvantages, we started to think how we can have the benefits of each. One idea is to have complementary views. The idea of complementary views is to have different visual representations of the same data. Like in this example, the same network data was presented by a node link diagram and the adjacent matrix. So how can we create complementary views in the immersive environment? The easiest way can be placing different views side by side. However, the user may only see one view at a time and must switch views frequently. Inspired from the results of our first user study, especially the different tilt angles for different visualizations, we designed a novel interaction technique to combine a Carplas map, a prism map, and a bar chart together. The user will first see a vertical Carplas map. Once the user tilts the map to a certain angle, it continuously morphs to a prism map. It then becomes a complete prism map with more tilting. When the user tilts more, the prism map shrinks to bars on the map. And finally, all the bars will move to the same plane to form a bar chart. Let's see how it works in a continuous and interactive way. Additionally, the user can also stay at any intermediate stage. The transitions are also bidirectional, so the user can also change it from a bar chart to a prism map and then to a Carplas map. We call this interactive technique tilt map. We also considered another way to have multiple views. Basically, the user can click buttons to change the view. To understand which method is more effective, we chose to only test the more complicated task and use the data of US and EU. In the US data, we use 5 states as the targets, and in the EU data, we use 10 areas as the targets. We again control the Morse eye for spatial correlation. Let us straight to the results. We found tilt map had some advantage of accuracy over side by side and was slightly faster than toggle. When we split the results into different datasets, we have some interesting findings. In the small dataset, the benefits of tilt map is more obvious, while in the larger dataset, such benefits were negligible. We suspect that is because participants were able to track 5 objects in the small dataset for tilt map. When we enlarge the dataset, 10 objects might exceed the upper bound of the human working memory. We also identified common strategies used by our participants. We used representative trials to demonstrate the strategies. The x-axis is the normalized time for a representative trial. Different color stands for which view the participants was looking at. The first strategy was only looking at Carplas map and the bar chart. In the second strategy, we can see participants frequently switching between views. In the third strategy, participants spend significant time on the transition. It seems some participants relied on intermediate views, for example, the bars on the map, to complete the tasks. The last common strategy was basically spend roughly equal time with Carplas map, prism map, and bar chart. We also identified strategies for other conditions. Please look at our paper for details. Lastly, our participants liked the design of the tilt map. We also found participants felt less confident in toggle than in the other conditions. Many participants also commented tilt map to be intuitive and cool. They also liked the way it provides a new and easy way to switch between views. In summary, we conducted the first user study comparing Carplas map, prism map in the immersive environment. We designed a novel interactive technique that combines multiple complementary views in the immersive environment. We also systematically evaluated our novel technique, tilt map, comparing to side-by-side and toggle. Thank you very much for your attention. I'd like to take any questions.
Great, thank you very much for that. Really interesting study and some very nice interactions there. I've got a question about about using a 3D immersive environment, because it's worth exploring that space because it's interesting and it's more accessible, but it still has quite a lot of overhead, I think, to people using it. So I wondered if you could apply any of your findings to 2D ones, for example, having a coordinated view where you can select places and see a bar chart of the values.
That's a very good question. I think currently the VR AR headsets are still not very cheap and also not easily accessed. However, we believe the VR AR headset will be much cheaper in the future, and also people like with much better rendering qualities. I think the two different medias definitely offers different fidelities and things like on a 2D screen. I think it's really difficult to use a tilt map and as well the prism maps as well. Like we have the well-known issues with occlusion and perspective distortion. So to be honest, I think this technique probably is not going to work well in 2D screen settings. I think you mentioned the multiple coordinated view to say if that works better. Is that part of your question? I think it can be very interesting to explore this direction as well. Yeah.
Okay, thank you. Another question is that people found the technique cool and novel and exciting. Is there a good way of separating opinions of people who like things because they're cool and novel and new, and people who like things because they are helping them address the task better?
This is an issue actually we discussed in a very recent IA immersive analytics workshop. So we discussed this kind of ground challenges in the immersive analytics. So there can be some novelty bias. So people think this is new and this is cool, so they rated it higher. This is something probably is not easy to fix in the near future. I think the thing we can do is we provide sufficient training to the participants so they get familiar with every conditions. And even better, we can do a long-term user study instead of a short one. We can do a study in like 5 days or a week or even a month. Then people are actually will be less biased by this effect, I guess. Thanks.
Thank you very much. Okay, thank you. Okay, let's move on to the next paper. So the next paper is called Phoenix Map, and Jan will present an interesting abstraction of 2D spatial distributions, and the purpose is to facilitate more comparisons and more distributions than normal heat maps allow. So let's see the paper now.
Everyone, I'm Junhan Zhao, PhD candidate at Purdue University Computer Graphics major, and presenting our recent research outcome, Phoenix Map, an abstract approach to visualize 2D spatial distributions. This work is co-authored by Xiang Liu, PhD student from Purdue, and professors Chen Guo, Zhen Yujian, and Yingjie Chen from James Madison and Purdue University, respectively. This paper has been published on IEEE TVCG in October 2019. The rich data captured is full of information and can be crucial for analytics practice and decision making. Often, people need to determine how a distribution changes over time or compare distribution in multiple instances. However, due to the conflicts between the limitation of display area and the large amount of comparative distributions need to visualize, the current methods are always restricted. The most popular visualization is combining heat maps with animations or small multiple techniques. Popular visualization methods for spatial distribution often utilize colors to directly encode the data attributes, like densities and time series, then plot spatially. Most of the approaches can be considered as variations of heat map. Some methods also seek for solutions by abstracting data, like Bristol maps. Additionally, Interesting topics like off-screen visualizations are emerging. Different projections are aiming to map the off-bound objects into the display area for visual comparisons. However, these approaches may meet visual clutter or difficulty to implement if the number of the distribution is large. Several research challenges when visualizing multiple spatial distributions with a heat map or small multiples. First, due to the limited screen size, the visualization dimension in each cell of small multiples may not display sufficient details. Secondly, it is also cognitively challenging to compare visualizations across multiple cells. Thirdly, when the amount of the distributions increases, visual cluttering causes perceptual confusions. These observations encourage us to come up with a solution by abstracting the visualization, Phoenix map. It allows us to visualize multiple spatial distributions in a concept form and enables overlapping to save the display space. Phoenix map is contributing to 4 aspects. It focuses on presenting 2 fundamental properties, the range and the density of spatial distribution, in an abstract way. It also allows the users to perceive and compare spatial distributions data efficiently. Next, it frees up a graphical space with a concept form that can provide a broad visualization design probabilities like overlapping. In the end, it provides a good quantitative perceptual estimating capabilities given the proper legends to the users. We developed a website for demonstrating the application of Phoenix map using VIS Challenge 2018 dataset. In the application, we can see Phoenix map can visualize the spatial temporal distributions by simply overlapping multiple graphs together. The visualization saves the display property while maintaining the transparency that the users can see through the visualizations and obtain additional insights from the base map, like geographical infos, water, and transportation systems. With respect to data aggregation, our method first requires an outline to surround the data points. There are numerous modern methods capable of computing an outline. For demonstration purpose, we selected a concave hole method for computing the edges. Offsetting the boundary towards the outside allows us to include all the dots on the original outline and use a place for visual encoding. We extract the control points of the new outlines and compute a closed Bezier curve. There are 3 reasons driving us to smooth the outline. Firstly, smooth outline is a real form existing in the nature. Secondly, it could accelerate and make the density computations accurately. Thirdly, literature suggests that users are pleased to perceive smooth curves. Since we intended to use width to present the density of the points enclosed by the region, however, in the distribution, density varies in different regions. We decided to break the outline into many segments, giving each segment a different thickness to represent the density enclosed by its corresponding region. For each segment, the user should easily see the density of the region represented by the segments without confusion. For any segments, we defined a region to count the numbers of the subjects. To gain the region, we first compute the maximum inscribable circle and use the 2 adjacent inscribable circles to encode one region. To convert the discrete graph to a continuous smooth curve, we applied a sliding window mechanism to smooth the zigzag segments. After this transformation, the width of the neighboring segments is averaged. We designed a legend to further represent the major distribution characteristics inside the region and to help on quantitative estimation. To compute the density legend, for each segment slice, we divide the slice into many subsections. With the text at the bottom of the legend, the user can easily see how many points correspond to the specific thickness shown in the graph and understand the characteristics of the distribution. There are 2 adjustable parameters influencing the visualizations, sliding window bandwidth and the number of outline segments. These 2 parameters are intrinsically relevant. Our experiments suggest setting sliding window size as around 1/10 of the total outline segments. More segments may return refined outline, but also increase the computational complexity. We designed and conducted 3 experiments to examine our hypothesis. Users can determine the variation of the density distribution using Phoenix map. Users can distinguish densities at different locations with the distributions using Phoenix map. The users can also quantitatively estimate the densities using Phoenix map with legends. We selected the dot map and the heat map as comparisons to evaluate the efficacy. There are 52 college students participating in this survey. All the experiments are tested online with a web-based setup. In the training round, we firstly introduced how Phoenix map computes in a high-level conceptual way. We don't expect the participants to understand the mechanisms, but the intuition. The participants received 24 random ordered graphics, visualizing 8 different distributions in dot map, heat map, and Phoenix map. The users are asked to link the graphics visualizing the same distribution together. For illustrating purposes, all the distributions are bounded in irregular geometries like a circle or rectangular. They are simulating the usage in real-world scenarios like visualizing agents' activities in a room. In Experiment 1, there are 2 matching tasks. The users are required to match the distributions visualized in dot maps to heat maps or Phoenix maps. Task 2 is a ranking task. The users are required to rank the densities of the circled areas from different distributions visualized in different methods. In Experiment 3, the users will receive either Phoenix map or heat map visualizing different distributions. Users are required to estimate the densities for all the circled areas given legends. For Experiment 1 and 2, since they are matching and ranking tasks, we use Wilcoxon-signed ranked test and Spearman rank correlation respectively for measuring their performances. In conclusion, we can see that the users were able to identify spatial information regarding outline and distribution densities from Phoenix map and heat map. When the distributions share the same outlines, Phoenix map can help the users to distinguish the differences better than heat map. We applied a man-Whitney U-test to examine the results in Experiment 3. There are 1,088 data entities in total collected from all the participants. A very small p-value suggests that the users can use Phoenix map to quantitatively estimate the densities within the distributions more effectively and accurately than using heat map. We also conducted a qualitative survey after the 3 experiments. Based on these results, we can conclude that the Phoenix map presents at least equally well as the heat map when visualizing spatial data with respect to distribution and range. However, Phoenix map is more concise and allows the user to develop a design by overlapping multiple maps together. Taking the advantages of a Phoenix map, the users can visualize multi-scale distributions with one graph for comparison. This approach can effectively reduce the visual clutter issue and enable subset visual explorations. Furthermore, since the Phoenix map is encoded in a basic consensus form, users can have more flexibilities to customize the color and pattern combinations when comparing multiple distributions in multiple Phoenix maps. This could potentially serve off-screen visualization when the aim is for completing the off-bound comparison tasks. There are still some limitations for the current status of Phoenix map. Phoenix map exploits the outline to encode the data density. It introduces a lack of precision to the exact locations of each data point. Adding system interactions like mouse over or click to view the dots details may help. Practically, the distributions being mapped may distribute with the gaps, holes, and being separated into different subregions. Phoenix map could be integrated with additional visualization techniques for indicating the spatial occasions or utilize other boundaries computation algorithms. For more information, please refer to our full manuscript on Attribute Explorer site. Thank you for your listening. Wish you have a nice day and enjoy the conference.
Thank you, Jan-Henrik. Really interesting paper. I really like the way that you abstracted these densities. One question I have, though, is that in a way you're showing the distributions inside out because you're putting all the information about the distribution on the outside of a distribution, which generally has fewer lowest densities. So how sensitive is your method to the convex hull, and what do you do with outliers or areas of very low spatial density?
Right. So actually in our demonstration, we use a concave hull instead of a convex hull. And the first question, the answer will be, if we use a convex hull to solve the problem, the algorithm would be not that sensitive, would be very robust, just because we were thinking about different algorithms. We can use a median axis, we can use a similar so-called, let's say, a straight skeleton, but those things computationally kind of cost more than what we are doing right now. So, and the other question, if we're talking about the outsider, like subjects, which are like less dense, with a less density, I think that that has to come up with some additional sort of a process regarding how we can summarize the data, because it's more like a radiational sort of like some data summary. And in that case, in order to create a comparison between the inside and the outside, we may have to do some additional approaches. And of course, the algorithms will be various.
Okay, the technique, obviously you lose a lot of spatial information there because you're abstracting to the side. So I guess the answer to the next question is no, but can it help people determine different scales of density, for example, bumpiness of surface?
Really good question, like different scale. So far that I would say like the density base is more like we calculate the percentage of the subjects contained in each square or unified unit or area. So in that case, regarding the scale wise, if the density performance is similar, then probably the Phoenix map will have the similar result. So I'm not sure if that answers your question.
Okay, that's okay. Great. Well, thank you very much. We'll move on to the next paper now. Thank you.
Thanks.
So the next paper, the last paper in the session, will be given by Ben Jacobsen, and it's on visualizing sets using a metro-like representation.
My name is Ben Jacobsen, and today I will present MetroSets, a modular online system for set visualization. This project was a collaboration between myself and my co-authors, Marcus Wallinger, Stefan Koborov, and Martin Neulenberg. Analyzing the structure of overlapping sets is a difficult problem which arises naturally in many contexts. The input to this problem is a collection of sets, which each represent some sort of attribute or category, as well as a collection of elements, which each belong to one or more sets. For example, our sets might be genres, while our elements might be movies. With this information, we would like to answer questions like, which set contains the most elements? Or, which elements belong to both of these sets? Or, how many elements only belong to a single set? This analysis can be aided greatly by effective data visualization. However, visualizing set systems is very challenging to do well, and tools for set visualization inevitably make trade-offs which make them less well-suited for certain applications. Perhaps the most well-known style of set visualization is the Venn diagram, and its close cousin, the Euler diagram. Although these types of visualizations are intuitive and easy to understand, they do not scale well, and cannot be used to visualize more than a few sets at once. Visual analytic systems, such as Upset, make it possible to work with much larger datasets. However, the scalability often comes at the cost of a non-trivial interface and less intuitive visualizations, which require training to interpret and navigate. We are interested in datasets which fall in the middle, too large to be visualized with Euler diagrams, but not so large that they require a visual analytic system. Naturally, we are not the first researchers to explore this area. Systems like line sets or bubble sets are also designed for medium-sized datasets, with around a dozen sets and 100 or so vertices. However, these overlay-based systems assume an underlying geographic space or geometric embedding, where fixed positions for the elements are given as input. In contrast, MetroSets does not make such an assumption. Computing and optimizing element positions is one of our major goals. In recent years, several researchers and artists have explored visualizing these medium-sized set systems using the metro map metaphor, whereby sets are visualized as metro lines, elements are drawn as metro stations, and elements which belong to multiple sets are drawn as interchanges. This approach has several advantages. Many people already intuitively understand how to read metro maps, and so relatively little instruction is required to interpret metro map drawings of abstract data. In addition, it scales comfortably up to datasets with over a dozen sets and hundreds of elements. The difficulty is that these visualizations are almost invariably made by hand, which requires both expert knowledge and a considerable investment of time. Our contribution to this field is MetroSets, a modular, online platform which automates the process, allowing users to quickly generate attractive MetroMap visualizations of their data with the click of a button. In developing MetroSets, we were guided by several design goals for the final visualizations. One reason for the success of real-world MetroMaps is the distinctive and immediately recognizable style with which they are drawn. For this reason, we place a high importance on matching these stylistic conventions, creating visualizations that allow the viewer to leverage their knowledge of MetroMaps to improve their understanding of the data being visualized. For example, we would like our drawings to have angles that are multiples of 45 degrees, easy to follow line trajectories, uniform edge lengths, easily distinguishable colors, and so forth. Another type of design goal is associated with the algorithms for extraction of the support graph that represents the set system. For example, two overlapping sets should be drawn with simple lines running in parallel without repeatedly splitting and rejoining. This sort of goal would make no sense in traditional MetroMap design because it involves the geography of the metro system. But as we deal with abstract input that does not contain underlying geography, we have the freedom to optimize this, as well as other desirable goals, such as extracting planar support graphs and preventing hairball-like subgraphs. This is how the MetroSets pipeline works. First, we upload the dataset, which we model as a hypergraph. Hypergraphs generalize simple graphs by allowing edges to contain any number of vertices. In the hypergraph model, elements in the dataset correspond to vertices, and sets correspond to hyperedges. As a pre-processing step, we simplify the input hypergraph by temporarily discarding all vertices which belong to a single hyperedge, and merging together vertices that belong to the same hyperedges. This helps reduce the size of the problem while preserving the essential structure of the input. For step 1, we then extract a path-based support. This is a simple graph in which each hyperedge is replaced by a path which travels through its vertices. This is the first step towards what will eventually become metro lines traversing through stations. In step 2, we re-expand the condensed hypergraph by expanding the merged vertices. We also reintroduce the single set vertices discarded earlier. By adopting different strategies for where these single set vertices are added, we can control how concentrated or spread out the stations will be in our final map. In step 3, we embed this graph in the plane. During this step, we optimize several desirable properties, such as minimal edge crossings and monotone metro lines. The output of this step is analogous to the geography of a real-world metro system. We know the basic positions and connections of the stations, but their positions in the final map are still undetermined. In step 4, the initial embedding is modified using MetroMap schematization techniques in order to straighten the metro lines and line them to octilinear slopes, and generally make the map conform to the stylistic conventions of real-world metro maps. Finally, we perform post-processing, such as determining the best order for the lines along each edge and placing labels to minimize overlaps with other elements of the visualization. For each of these 4 steps, we implement 2 or more algorithms, allowing for different optimizations and combinations of optimizations. For ease of use, we also provide 3 preset pipelines, which we empirically found to produce high-quality MetroMaps on a wide range of inputs. Let's see MetroSets in action. We start by clicking on Create. From here, we can either upload our own dataset or else use one of the provided example datasets. Let's use the Simpsons dataset, where elements are characters from The Simpsons, and sets are attributes like school or blue hair. Once our data is uploaded, we can choose a preset pipeline to use. For now, let's stick with the default. To focus on just one line, we can hover over it with the mouse, highlighting all the stations it traverses. We can also hover over the name of the line and the legend to highlight it in the map. We can also hover over a single station. This highlights all of the lines incident to it, along with the stations they contain. This makes it easy to tell if 2 elements share a set. Statistics describing the dataset and the created MetroMap are provided on the right-hand side of the screen. Hovering over each statistic gives more information on how to interpret it. Hovering over a specific line on the map or legend shows the number of elements in that set, making it easy to determine the cardinality of different sets. Metro sets also offer support for more complicated set operations. To use these, we open the settings on the left-hand side and navigate to the exploration mode. Suppose we want to know how many characters are both evil and work at the power plant. To investigate, we select the intersection mode and click the two lines we're interested in, showing us all the characters which fall into both categories. To make further queries, we can either reset our selection or choose a new exploration mode. Using the union mode, we can select any number of sets to highlight all the elements which belong to at least one of them. Here, we can see all of the characters who have blue hair or go to the school. With the complement mode, we can instead choose any number of sets to remove from our selection, highlighting all of the elements which don't belong to any of the chosen sets. Here, for example, all of the non-evil characters are highlighted. With the use of these interactive tools, MetroSets provides support for 15 of the 21 set and element-related tasks identified by Ocelot et al. In their 2014 survey of the state of the art in set visualization. Finally, we can save the MetroMap as either a PNG or SVG file. We mentioned before that we have implemented multiple algorithms for each step. Let's see an example. Once again, we use the Simpsons dataset. This time, however, we select Expert mode. This lets us select each pipeline stage separately. Let's change a few of the options and see what happens. As we can see, the resulting map looks quite different, despite using the same dataset. By changing different pipeline steps, we can experiment until we find the visualization that best suits our goals. Earlier, we described our design goals for metro sets. To evaluate these design goals in a rigorous fashion, we've developed several quantitative metrics for MetroMap drawings, which let us automatically evaluate the performance of each combination of pipeline steps on a wide range of different inputs. These metrics represent a combination of the traditional and novel goals we discussed. For example, we measure the octolinearity of a drawing, which is the extent to which all of its angles are multiples of 45 degrees. Meanwhile, the consecutive ones metric counts the number of times that two lines run in parallel, split apart, and then rejoin. This metric is a novel contribution, as measuring it only makes sense in the context of metromaps of abstract data. We present and measure other metrics similarly, and we've used them to perform extensive quantitative analysis of our system. In particular, we selected the 3 preset pipelines mentioned earlier by identifying combinations of pipeline steps which worked particularly well together with respect to these metrics. Anticipating that the default balanced pipeline would be the one most people use, we subjected it to additional scrutiny. Using it, we generated just over 4,000 metromaps, ranging from 20 to 160 vertices, and 6 to 19 hyperedges. We then recorded the computation time required for each map using an ordinary desktop computer. These plots summarize our results. The plot on the left shows the median running time of metro sets as a function of the number of hyperedges in the input data, with each colored line representing inputs with the same number of vertices. From this graph, we can see that increasing the number of hyperedges within reasonable limits has little impact on running time. The plot on the right is similar, but swaps their two variables. It plots running time as a function of the number of vertices, and each line represents inputs with the same number of hyperedges. Empirically, this suggests that MetroSets has a runtime which is quadratic in the number of vertices, and that it can comfortably handle inputs of up to 140 vertices in under 10 seconds. The MetroSets system is implemented and fully functional. Source code, experiments, and datasets are available on OSF. Thank you for watching our video.
Thank you very much for the paper. They're really, really nice maps, and there are lots of nice comments about how good the map's used. I've got a question about the application. So you showed a demo where the application supported lots of different set tasks. Would those, say, bubble sets, would bubble sets be as effective at supporting those tasks? And is the main point to use a different visual representation?
In terms of like identifying the intersection or like union of sets, my intuition would be no, since like bubble sets, like all these overlay-based techniques assign primacy to the sort of like there's an implicit network structure to the data, right? Like there's positions for all of the nodes, and it doesn't try to optimize that at all. So like if you're visualizing using bubble sets to do, say, restaurants in a city, maybe there's an Italian restaurant over here, and it won't move them any closer together. Whereas in metro sets, all of the elements that share the same set membership, we're trying to put them very close together. So I think answering set theoretic tasks like finding union or intersection, I think should be much easier in our system.
Okay, thank you. Another question I had, let me just look at my questions, was order and position. So an advantage to not using geographic stations is that you can put things where you want and optimize the position, the layout. But could you encode ordinal data in the order of stations and two-dimensional data in the arrangement of the nodes, or would that just completely mess up your layout?
So we have experimented with putting ordering restrictions on the vertices. I think originally we had intended to allow users to specify partial ordering on the vertices. For example, maybe you're plotting like movies and genres are like your elements and sets, and you want all of the movies to be ordered by the decade they came out, something like that. That's definitely something that can be done. Like we can put it in as a constraint when we're determining the ordering of vertices on lines. If you put on too many of those constraints, though, then you start losing the metaphor in a pretty big way. Like you can end up with maps where there's lots of non-octilinear lines or things are crossing. It's just sort of trying to serve too many masters. So I think probably it would take more work to figure out how to do that in a way that was still like very visually pleasing for like larger data sets.
Okay, thank you very much. And that concludes the session. We've seen 6 papers on some really diverse abstractions of geographical and other graphical space. So I'd like to thank all the authors for keeping to time. Very good. And let's close the session now and enjoy the rest of the conference. Thank you.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Visualizing the performance progression of machine learning techniques is often achieved by plotting the accuracy in a line chart. For specific tasks such as multi-class classification, they hide important factors such as inner-class confusion and instance-level details. We propose Instance Flow, a tool for interactive visualization of the evolution of classifier confusion on the instance level.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau, answer questions at the speed of thought.
Hi everyone, I hope you're doing well. I'm Heikyu Park from Georgia Tech. I'm very excited to present Bluff, a visualization tool to interactively decipher adversarial attacks on deep neural networks. Deep learning is now commonly used in many domains. For example, in the medical field, deep learning models can estimate the treatment effects on patients. On the road, we can see self-driving cars using computer vision technologies. However, deep learning models are vulnerable to adversarial attacks. An adversarial attack applies carefully crafted perturbations on data inputs and fools a model into making incorrect predictions. Adversarial attacks jeopardize many deep learning-based technologies, especially in security and safety-critical applications, such as data-driven healthcare and self-driving cars. Due to the threats of the adversarial attacks, people cannot confidently use deep learning models. To overcome the vulnerability of deep learning models, we need to understand how the adversarial attacks permeate the model's internals. Also, for a better understanding about adversarial attacks, it would be worthwhile to examine if and how an attack strength changes how the model produces incorrect predictions. For example, it would be useful to know if a stronger attack exploits the same neurons as a weaker attack does, or if those sets are completely different. We present BLUF, an interactive visualization tool for discovering and interpreting how adversarial attacks mislead DNN into making incorrect predictions. Our main idea is to visualize activation pathways within a DNN traversed by the signals of input data. For given input data, an activation pathways consist of neurons that are highly activated and the most influential paths. Activation pathways represent what features are detected and how those features are related to contribute to the final prediction. To understand how the attacks manipulate the neurons and the paths inside the models, BLUF visualizes the activation pathways of both benign inputs and attacked inputs. That is, BLUF finds and visualizes the most activated pathways given benign and attacked input data. BLUF also visualizes the most inhibited paths by the attack to uncover where the attack is blocking the signals to the benign path. Also, BLUF visualizes the most excited paths by the attack to uncover where the attack stimulates to induce the activation pathways going towards wrong directions. The BLUF interface tightly integrates three coordinate views. It consists of control sidebar, graph summary view, and detail view. Here, a user inspects why a deep learning model must classify adversarial giant panda images crafted by the projected gradient descent attack as armadillo. In the main graph summary view, we visualize the activation pathways of benign and attacked input data. Here, each vertex represents a neuron. When hovering over a neuron, BLUF shows the detailed information of the neuron. The detailed view for a neuron shows a feature visualization and example data that visualize what feature the neuron is detecting. For example, for giant panda images, this neuron looks for face of animals that have white furs and dark eyes. Feature visualization is a synthesized image that maximizes the corresponding neuron's activation. Dataset examples are patches of images from the training data that highly activate the corresponding neurons. We also show how the neuron's median activation will change according to different attack strengths. Here in the graph summary view, the neurons are represented with different colors based on their roles. The green nodes are the most important neurons only for the original class giant panda, which means they are highly activated by benign giant panda images. The blue nodes are important neurons only for the target class armadillo. The orange nodes are the most important neurons for both original and target classes, giant panda and armadillo. The red nodes are the neurons that are highly activated by only successfully attacked images. These neurons are exploited by the attack to induce the incorrect prediction. By exploring the activation pathways, PGD successfully perturbed pixels to induce the brown bird features. an appearance more likely shared by an armadillo than a panda. Both armadillo and brown birds have small, roundish, and brown bodies. The brown bird neuron then contributes to the armadillo misclassification by activating more features such as scales, bumps, and mesh. By using the options in the control sidebar, users can interactively filter the neurons and connections to visualize. For example, they can select to visualize R graph, or only highlighted neurons, or only pinned neurons. By using the highlight pathways options, users can select which activation pathways to visualize, such as most activated or most inhibited, excited, or most changed by the attack. By using the comparison mode, users can compare how attacks of different strengths have different activation pathways. In summary, we developed BLUF, an interactive system to understand how adversarial perturbations flow of deep learning model. BLUF visualizes most activated, inhibited, excited activation pathways after the attacks, and provides flexible comparison of attack escalation. Thank you all for listening. I'm happy to take any questions.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Nowadays, data is often distributed and owned by different participants. There is an emerging need to provide a joint visualization, such as a TS&E projection, to serve as the full picture in data analysis. If the participants are privacy sensitive, how can we build a joint projection without data leakage? Conventional embedding algorithms, such as the TS&E, are designed for single-site computation and require data centralization. Privacy leakage may happen in 3 stages in the visualization pipeline.
Blockchain has gained more attention and its applications are emerging. We collect 76 blockchain visualization tools and systematically classify them into 5 aspects: target blockchain, blockchain data, target audience, task domain, and visualization type. In the end, we look at open challenge in blockchain visualization.